So here we go. And now I can't concentrate because a Miley Cyrus joke was made right before I hit the record button. All right, so I'm recording, yes. It's going to be on the video. All right, so I wrote down the, this just takes forever here. There we go. So I wrote down all of the learning objectives and essential knowledges and everything that's on that reading guide, okay? And I'm going to go through these very quickly because we don't have a lot of time here. And I want to have some time for actually working some practice problems at the end. But big idea one is one of the big ideas that's kind of covered in this reading guide. And this reading guide is basically talking about precipitation reactions and then a little on, I think it's just precipitation. Let me check the book to make sure. I don't think acid and base is until 4.3. But let me make sure. Yeah, so just general aqueous solutions and then precipitation reactions, which we talked about this last year, so this is still review. Once we get into 4.3 and 4.4, then this is a little bit more new, okay? So you really want to focus on those. But the big idea here, it's good to read over these. A lot of times they're not going to have like focused content on what we're really covering, but it's really good to know the big ideas as well. And one of the big ideas is elements, okay? And the way that elements interact with one another. And if you go down to 1E, okay, so we're going to focus on 1E here after we get through this other stuff. Yeah, I don't have a better way to do this. Actually, I probably do, but I'm not thinking of it. All right. So atoms are conserved in physical and chemical processes, so now we're getting more into the chemical reaction type stuff when you look at 1E, okay? And then once you get down to 1E2, now we're talking about stoichiometry, right? Okay? So now it's talking about chemical processes result in the formation of new substances, and the amount depends on the reactants, okay, as well as the efficiency of the transformations. Now we're talking about percent yield, atom economy, stuff like that. Okay? Once you get down to E, it specifically talks about gravimetric analysis, which is interesting because that's what we're about to do tomorrow in a lab. Gravimetric analysis, a substance is added to a solution, and what it does is it causes a precipitate to form. Okay? That's another way to say forming a solid, right? And then the mass of that solid, we can take the mass of that solid at the end after it has dried, and we can actually figure out either what we had initially or how much we had initially, depending on what really our question is. Now, the question for your lab tomorrow is going to be what is actually there, because it's an unknown. Okay? So that's kind of the idea behind gravimetric analysis. It's really a simple idea. You just add a couple of solutions together, you get a precipitate, and then you're going to measure the mass of the precipitate, and you can do some backwards stoichiometry to figure out how much of the reactant you had. Okay? So it sounds more complicated than it is. Learning objective 1.19, the student can design and or interpret data from an experiment that uses gravimetric analysis. If it's in the learning objectives, we should probably do a lab on it. Okay, so that's why we're doing this lab tomorrow. All right, so then we get into big idea number 2. That talks about chemical and physical properties, and it's talking about intermolecular forces and intramolecular forces a little bit here. So that's kind of the big idea on this second big idea. Not at all the best way to say that. So then it's talking about physical properties, okay? And then I like how it's talking about the relationship of the macroscopic to the microscopic. We're really going to be focusing on that a lot this year, okay? And then it talks specifically about solutions right here at the bottom. And it says of particular importance is the conceptual understanding on the molecular level of the structure and composition in a liquid solution. So then they're going to go into a little more detail about that once you get to 2A3, which is right here. Okay, solutions are homogeneous mixtures. Did we remember that? We talked about that at the very end of last year, okay? But a solution is a homogeneous mixture. That's actually just a synonym for homogeneous. So I guess we talked about that part at the very beginning of last year. but we talked specifically about solutions at the very end. Okay, so maybe that is sticking in your brain because it's the last thing we covered, or maybe because we went through it fairly quickly. There's not a lot there, but we'll go into a lot more detail about it this year. Okay, so then you get into 2A3H is specifically the one I wanted to look at right now. Generally, when ionic compounds are dissolved in water, component ions are separated and dispersed. The presence of ions in solution can be detected by use of conductivity measurements. So separated and dispersed. Do you remember the term that we used for separated and dispersed last year when we talked about it? Not dissolved. Okay, you have to be careful with that because dissolving, like sugar dissolves. I don't know if you remember us talking about this last year. We may or may not have. Sugar dissolves in water. Does sugar separate and disperse into ions in water? If you test the conductivity of sugar water, it actually does not conduct electricity, okay? Because it's not splitting up into ions because that's a covalent compound. And covalent compounds don't split apart into ions when you put them in water. There's another technical term for separate and disperse that we talked about last year. You're close. Okay, I would go with ionizing, okay, because that's essentially what's happening. It's technically called dissociation. Okay, so dissociation is when those ions split apart when you put them into water. Okay, now we watched the process a lot. You remember the horror film we kept watching last year where the salts got pulled apart by the water molecules? And it's just, you might have been, I don't know. All right, so point is, when it says separated and dispersed, that's a really, really important concept, and we're going to come back to it several times. You need to understand, when you put an ionic compound into water, typically, it's going to separate into its ions. That's called dissociation, or it appears that the AP exam is now going to call it separated and dispersed. Okay? Which maybe is a little more descriptive than dissociation, so maybe that's a good thing. All right, I just want you to be aware of their terminology on that. All right, so now on to big idea number 3. Oops.
Is there a search button?
I did pass it. Yeah, and you laughed. You were right. Okay, so big idea 3 is talking more about changes in matter. Okay, so this is, again, the fancy way, rearrangement of atoms. That's the fancy way of talking about actual chemical reactions. So big idea 2 really focuses on physical processes. Now we're talking about chemical reactions. Okay, and that's where we're going to really in my class, right? Yeah, I hate to tell you this, but I lied to you about wife swap. That doesn't really happen. So, sorry, we'll talk about that a little bit more. No, you can get a new wife. You just weren't swapping because the marriage was dead to begin with. The original marriage. Yeah, this is a metaphor. Yeah. This is not personal experience, I promise. All right. So 3A here, talking about chemical changes. Let's see. This is going to be a fun video to watch, I feel like. Okay, so this is just talking about stoichiometry. I don't think there's a lot that we need to really focus on there. But when you get to 3A1, okay, this is an important idea. Chemical change may be represented by a molecular, ionic, or net ionic equation. Okay. Now we are going to talk about that on one of the practice problems, or I guess the activity that I just handed out to you. The activity is entitled molecular, ionic, or net ionic. Okay, so you need to know when you should use each type of equation, what situation. Now, do we remember how to do molecular, ionic, and net ionic equations? Okay, we'll go back into that, and we should have about 15, 20 minutes at the end of class to talk about that. Okay. 3A1B. Depending on the context in which it is used, there are different forms of balanced chemical equations used by chemists. So that's basically just saying you need to know when to use these 3 types. Okay. This is not going to make a lot of sense until we see some examples. And then learning objective 3.2. It says you need to be able to justify the choice of equation type. So because that's a learning objective, that's most likely something that's going to be on the AP Chemistry exam, a question like, for this situation, what would be the best type of equation to use, the molecular, the ionic, or the net ionic? And you have to choose and explain why. Okay, so we're going to do that a little bit today. That's good for big idea 3. And we got to go all the way to 5. We'll just skip past 4. Oh, I feel like it's Price is Right here. Oh, I went too far.
Again?
Okay.
Your pet is terrible at this.
Yeah. All right, so big idea 5 is talking about energy, the energy that associates or accompanies these chemical changes that will happen, and sometimes physical changes that will happen, okay? So then we go down to 5D. You're getting a whirlwind tour here. It's going to make you dizzy watching this video.
You could blow in the microphone.
Yeah, I'm not going to do that. That would hurt people's ears. Right. Last year I was making a video, the fire alarm went off, and I was making videos for all the AP students, so they had to watch the videos, right, in order to know the content. And so several of them came back the next day and they were like, that scared me to death, you know, because all of a sudden it's like this really loud noise. So, all right, so anyway, enduring understanding 5D, it says electrostatic forces exist between molecules as well as between atoms or ions. Now, electrostatic forces between molecules, what do we call that?
Electrostatic forces.
Say it again. Right.
I was going to say
It's
that.
the forces between the molecules, right? Okay, so that's intermolecular. And they're saying basically electrostatic forces really determine both intermolecular and intramolecular, right? Which we already kind of talked about this. That makes it a little tricky to decide what is an intramolecular force and what's intermolecular, right? So then if we go to 5D2, at the particulate scale, chemical processes can be distinguished from physical because usually you can distinguish chemical bonds from intermolecular ones, okay? But there's that one example that we talked about when we were talking about physical and chemical changes. You remember that, where we talked about an ambiguous change? So say physical change, a chemical change, or an ambiguous change. This is the gray area, all right? So you've got your, this is obviously a covalent bond, right? Where this is obviously a London dispersion force, right? So this is a weak intermolecular attraction. But somewhere in the middle, there are these strong attractions, like the ion dipole attractions, when you dissolve an ionic compound in water, and they're almost as strong as covalent bonds sometimes, as far as the strength of their electrostatic forces. So it's really hard to decide, are these really, you know, intermolecular forces, which is how we usually define them, or are they intramolecular? And so a lot of times we'll call these ambiguous, okay? So the ion dipole forces especially, you just need to understand they're kind of right in the middle of the continuum. They're the strongest of the intermolecular forces, but they're not quite as strong usually as the intramolecular forces, but they're close, all right? I just want you to, so actually there are people who argue that dissolving of a salt is a chemical process. We won't usually think of it that way, but there are people who will argue that, okay? All right. And then very quickly here, big idea 6. Oops. Yeah, big idea 6 we're really not going to talk about a whole lot yet because that's equilibrium, so we're going to really focus on that one second semester, okay? But when you go to 6C, there's something that's a little bit relevant here. Chemical equilibrium plays an important role in acid-base chemistry and solubility, which, again, we'll talk more about that later. When you get to 6C3, here we go. 6C3D, okay? Just this one little statement right here is going to make your life easier. All sodium, potassium, ammonium, and nitrate salts are soluble in water. Memorization of other solubility rules is beyond the scope of this course and the AP exam. So last year, I gave my students a fairly lengthy list of solubility rules they needed to memorize. You don't have to do that anymore.
So it's like each X means things that they took out.
Right. Yeah, so the X's are, they're called exclusion statements, and they're saying you don't need to worry about this anymore, okay? Yeah, I actually never made you memorize them in Honors Chem, but in AP Chem, up to this point, you've had to memorize these, okay? But you do have to memorize these, okay? Sodium, potassium, ammonium, and nitrate salts. You need to remember, those are, in the way we talked about it last year, those are the losers, right? Those are the ones who never precipitate with anything ever. No one wants to be with them, okay? And so those are the ones that are always soluble in water. They will always stay dissolved in the water and never form a precipitate, okay? If you remember these, and it's just 4 things right here that you have to remember. If you remember those, that's all you need to remember for the AP exam. Therefore, that's all you need to remember for my test, okay? All right, so those would be good ones to remember. And I think that's probably good enough, so we'll spend the rest of the time just going through some of those molecular ionic, net ionic equations, okay?